Okay.
Oh, I guess I just have to hit this button. Sorry. Okay. Okay. So I just wanted to try to make a quick comment here about me as the audience to your discussion, your exposition of this tenfold way stuff, which is that one of the things that I got interested in was when you said that it connects to Cartan's classification of compact symmetric spaces. And so I brought up some very naive ideas about that, partially based on discussions between you and me a long time ago about stuff like that. And it was like, I can't remember what this week's finds it was, what number it was, but there was this discussion about the diamond cutting approach, meaning you look at the, what do we call that thing? The root system, the kaleidoscope, and you sort of slice it up in certain ways. And so there's fun stuff that we've talked about before about how that relates to symmetric spaces at various times. But after we talked about that just last week or whatever it was, I realized that I'm really confused about the relationship and the contrast between compact symmetric spaces on one hand and non-compact Hermitian symmetric spaces on the other hand. Partially because, I have this vague memory that it's actually even a little bit better than vague, that the Hermitian symmetric spaces, which I think tend to be non-compact, they really correspond to those Jordan triple systems. And it's those Jordan triple systems that we were discussing in the language of diamond cutting and something like that. So this is just an admission, not exactly an admission of error, an admission of confusion. I'm really confused. If we do try to go back and really look in detail at that, there's something I'm confused about that, which is the contrast and the relationship between, on the one hand, these compact symmetric spaces, and on the other hand, some kind of non-compact symmetric spaces, very likely Hermitian symmetric spaces, and how all those might relate to Cartan's classification, might relate to the tenfold way. But this was all based on, very naive ideas, very naive recollections of mine. So it's not surprising if I'm confused and ignorant. But do you have any comments about that, or basically that you're saying both that I am?
I really don't understand this stuff about symmetric spaces very well. I think I once understood it better. I guess like the one thing that I do know is that you get a symmetric space from a Lie algebra with you could say a Z mod 2 action on it or a Z mod 2 grading on it. They're, I guess, the same. And then you use the stable, you use the fixed points of that action to be the stabilizer.
Yes.
So
that's very helpful. Yes, go ahead.
But everything having to do with the root systems, like how do you identify those sub-algebras, those fixed point sub-algebras in root systems, from root systems, I don't understand. And I was trying to look it up in Helgeson's book on differential geometry, Lie groups, and symmetric spaces. And I realized that, like, I took a course from him on Lie groups once upon a time using that book. Never got to the symmetric space stuff. And I was thinking, okay, he's a very systematic guy. This should be a good way to learn about it. And I found it really hard to quickly get the information out, because in some point near the end of the book, he starts saying, we're going to classify the symmetric spaces of types A, B, C, and D. And then I had, and they're not A, B, C, and D in the Dinkin diagram sense, but like some complete, just some kind of way of talking about different kinds, like compact, non-compact, or something. But I had tons of trouble even finding where these types were defined. And I had imagined that there was some way you could look at a Dinkin diagram and draw color the dots on it in some way that would.
That sounds very plausible. Yeah.
Things. but I didn't see anything like that instant, at least not in my brief look at that book. So I left
Helgeson's book, yeah.
sort of discouraged. I know that there's this book by Bessa. There's a pseudonym of a bunch of French folks named Bessa,
Yes,
who they claim is some relative of Bourbaki.
right, right.
And he has, I think Bessa may just have one book, and it's on something like Einstein metrics, but it has
Something
a big
like that, yeah.
section on symmetric spaces, and it says one of the things that's going to be good about this book is that it'll have tons of tables and charts, and so it does.
Oh, that could be good.
And so I feel like grabbing that and just trying to, if they have these symmetric spaces organized in some way that helps me understand like how you get them.
Okay. So, I mean, I thought you did give a really helpful, some very helpful hints about how, if we really did try to understand it, how these symmetric spaces would work. And, starting out being homogeneous spaces, and then you put something extra on them, and you have all these homogeneous spaces that you're relating to the tenfold way and stuff like that. And
yeah, there is stuff I do know about that. That isn't what I mainly want to talk about today, but I'll just mention that the way Milnor gets these symmetric spaces from Clifford algebras, or that eightfold and twofold Bott periodicity.
yes.
I was mainly focusing on the eightfold case because it's sort of more exciting. The way he says they're symmetric spaces, and the way he shows it is really efficient, because he describes them all as subspaces of ON. So they're all just subspaces of different ONs. And so the symmetric space structure on ON sort of restricts to a symmetric space structure on these.
Yeah, that could make it nice and easy.
So for those, he doesn't need to, anyway, so that's nice. But that has nothing visibly to do with Dinkin diagrams. You don't need to know about Dinkin diagrams to understand what he's doing there.
Yeah.
But you would need to know something about Dinkin diagrams to know why there are only these 10 series, because only with Dinkin diagrams, I imagine, could you make sure you've gotten all of them. So
right. Okay, so I just wanted to bring that up as, for potential future projects. I just wanted to, again, make it clear that there's things I don't understand going on there. But okay. So you're going to start now?
Yeah, I'll start.
Okay.
Share my screen. I'll full screen it. I always have to do it twice. Okay, so yeah, so I list here 4 different tenfold things. So one is rather vaguely stated, which gets more precise later: ways that Hamiltonians can get along with time reversal and charge conjugation symmetry. So this is actually how physicists thought about the tenfold way, or came up with the tenfold way in the 2000s.
And somehow it's supposed to make me think of types of matter or something like that.
Yeah, and there were condensed matter physicists doing this, and they actually were studying particular kinds of Hamiltonians that would tend to show up in condensed matter physics. Then second one is associative real superdivision algebras. So I think of that as a very fundamental one. Then a third one is the 10 different kinds of real and complex Clifford algebras, where we call 2 Clifford algebras Morita equivalents if they have the same. We'll think of them as, well, I'll say more about this, but we'll think of them as super algebras, and we'll say the Morita equivalent if they have the same categories of or representations on super vector spaces. And so that actually was sort of brought in by this topologist named Wall, CTC Wall, in 1964.
That's the third one.
Yeah, the third one. And he like almost could have come up with a second one, but I don't quite know who came up with the second one. Dolan talked about the second one. I mean, yeah, but I'm not sure he's the first to have done so.
Okay.
And then there's this fourth one, which we were just sort of hinting at, classical families of compact symmetric spaces. So I'm not going to talk about that one at all in this talk.
Okay.
That I hope someone's going to invite me to give another talk and I have to talk about.
Sure.
So we're just going to skip that stuff.
Okay, so these are all tenfold ways, but we think that they're actually all secretly the same tenfold way, rather than 4 different tenfold ways.
That's right. There's supposed to be a canonical bijection.
And except that the canonical bijection may sometimes be slightly ambiguous as to upside down or something like that.
Right. So in our previous conversation, I pointed out that I found like 2 different ways, 2 different canonical bijections between item 3 and item 4. And that's one of my mysteries that I still want to sort out.
Right. I mean, but it is, obviously it's coming from some sort of canonical bijection between one of them and themselves.
Okay, yeah, that's a good.
Some sort of opposites or something.
Yeah, that is a good way to get out of it. Get out.
Okay.
Yeah. So Gregory Moore has an interesting puzzle and a footnote in his paper of his. He has like course notes on such stuff, and he noticed that Dyson in his old paper on the threefold way actually alludes to a tenfold way, a tenfold classification, which is different than these ones that I've mentioned here, and which people seem to have overlooked.
That Dyson hints at this or talks about this where?
So Dyson has a paper that I think is called the threefold way, or it's the paper that introduced the threefold way at the very least in 1964. And there he was pointing out that the classification of irreducible representations of groups, complex representations of groups, into 3 kinds is important in physics.
Yes.
And he was like relating it to various things. But he also mentions a tenfold classification of I think of like representations of groups as unitary and anti-unitary operators. And so anyway, I don't want to get into it too much, but he has another tenfold way, is the point. And so Gregory Moore asked the question, like, is this tenfold way the same as these other ones? And then as a footnote, he says, in case you don't understand what I'm talking about, notice that I also have 10 fingers, but that doesn't mean you can answer the question like, which Clifford algebra corresponds to my right pinky finger? So that is his attempt to precise the concept.
Have you thought about that?
Have I thought about that?
Yeah.
No, but I
well, it's obvious. Obviously, the thumbs correspond to the complex one.
Okay, well, there you go. You're just thumb biased. You say obviously the pinkies do, but okay, yeah, okay, yeah, it's true. Okay, well, no, I won't attempt to do that. My crackpot theories are focused on trying to get a relationship between the 8 trigrams in Chinese Yang theory and the 8 real Clifford algebras. That is more promising.
It is. It's less challenging. Yes, go ahead.
Okay. So here what I'm trying to do is like motivate everything from physics. And so I remind folks that pure states in a Hilbert space, you aren't exactly unit vectors in the Hilbert space. that is, from some point of view, the best way to think of a pure state is it's an equivalence class of unit vectors where two are count as the same if they're one of them is the other multiplied by a phase. And so the set of these things is the projective space of the Hilbert space, which of course you could also think of as a space of lines in the Hilbert space through the origin. So a lot of sneaky stuff in physics comes from this difference between the naive idea that it's the Hilbert space that counts and like the more sneaky idea that it's the projective Hilbert space that counts. And so one of those sneaky twists is this theorem that Wigner stated in 1931. Here, since this isn't my official talk, I get to like say all the stuff I don't say in the talk. So apparently his proof is extremely sketchy, and it was Valentin Bargmann who like wrote down a detailed proof later. But anyway, this is always called Wigner's theorem. And so it says that any map from the projective Hilbert space to itself that preserves transition probabilities has to come from either a unitary operator or an anti-unitary operator.
Okay.
Yeah. One thing I want to do is like come up with a really nice proof of this. And I'll just tell you like a really brief plausibility argument for it, which is this transition probability business, this absolute value of the inner product of two vectors squared. So from that transition probability, you can actually cook up a formula for a metric on the projective space, which is the Fubini-Studi metric, the usual maximally symmetric.
Yes, sounds very plausible, yes.
So you just have to apply some kind of function to the absolute value of the inner product, and you can get the distance between 2 points. If you have a good mental image of projective space, or at least like so CP1, you can sort of imagine that something like that would be true. And so then any map that preserves transition probabilities has to preserve the metric on projective space. And because of the way metrics work, those only metric preserving, there aren't that many metric preserving transformations. And in particular, like if a metric preserving transformation fixes a point, then it's determined by its action on the vectors in the connected manifold. And so in other words, we're in a very rigid situation.
Say that once again. If what? If it preserves 1 point, then what?
If an isometry of a connected Riemannian manifold preserves a point,
Yeah.
then it's determined by its action on the tangent vectors of that point.
I very much agree, but I think the audio must have cut out because I didn't hear you say that. Okay, go ahead.
Okay. So the possible maps from the projective space to itself that preserve transition probabilities are very limited in scope, and so you just then at this point it becomes fuzzy. so then you have to somehow like convince yourself that unitaries are giving you like the identity component of this group, but then there's like another component, which are the anti-unitaries.
That's interesting. Okay, yeah.
Like a sort of like a reflection-y kind of thing.
Yeah.
So that's how I would try to prove it if I had to prove it. But it would be nice if it would be like a really, really slick way to fill in everything. The proofs I've seen are not very nice. they take
Right.
Okay, so I'm just going to use that, and then so it's fun to think about that when you have symmetries in physics that square to the identity. And there are three super important famous ones: parity, charge conjugation, and time reversal. And symmetries could be symmetric or not under these putative symmetries. And sometimes they're symmetric only under combinations of them. So like the standard model is not even invariant under CP or PT or CT. It's only invariant under CPT. But there are lots of physics you can make up that are like symmetrical under like combining, switching particles and antiparticles and reversing the direction of time. So there are lots of, well, so besides CP and T, we get these other possible symmetries. And the part of the point is the symmetries may or may not be present, but when they're present, we have some physical interpretation of what they are.
Sorry, let me just try and, okay. Time reversal, that seems pretty obvious. Parity, what's parity? I mean, I should know, but yeah.
Reversal. It's space reversal.
Space.
Since we're in
like parity, yeah, go ahead.
Yeah, since we're in an odd dimensional space, you can get a nice representative of the other component of the orthogonal group by setting x, y, z to negative x, negative y, negative z. So that's what we take to be parity. So just complete spatial inversion, sometimes people call it. So P, and so like the full Lorentz group in 3+1 dimensions, it has 4 connected components. And one of them contains the identity, the other contains P, the other contains T, and the other contains PT.
Okay.
So there's this important Z mod. It's also a Z mod 4 quotient group. It's also conveniently, you can implement it as a subgroup.
Mm-hmm.
And so charge conjugation is sort of different than those things because it involves some concept of particles and antiparticles or electric charge.
Yeah, so I'll think about that, but okay.
So these are, okay, so now suppose you've got a map from the projection of a Hilbert space to itself, preserves transition probabilities, and suppose it squares to the identity. So it's a physical symmetry that squares to 1. So what can it be like? So it's sort of interesting. So it could come from a unitary or it could come from an anti-unitary by Wigner's theorem. That's the only options. And because the map on projective space squares to the identity, the unitary or the anti-unitary has to square to a phase. It doesn't need to square to the identity, it could just square to a phase, because a phase acts as the identity on the projective space.
Yes.
So we have that dichotomy, but then they work differently, these two cases. Because if you have a unitary that squares to a phase, you can multiply that unitary by a suitable compensating phase to get a new unitary that actually squares to 1. And that new unit, and when you change the unitary by multiplying it by just a phase, you're not changing its effect on the projective space, because phases don't do anything on the projective space.
Yes.
So basically what you'd say is like, without loss of generality, we can just like fiddle around with our unitary so that it squares to 1 and has the same effect on states.
Okay, yeah.
And that's what people typically do. But in the anti-unitary case, it's much more interesting. Well,
Yes.
It's more interesting, let's say. Because for starters, I mean, you can still multiply the anti-unitary by a phase and you can get a new anti-unitary that has the same effect on physical states. But when you do that, fiddling, it doesn't change the square of your anti-unitary, because if you do a little mental calculation, when you multiply an anti-unitary by a phase and then square it, well, you get like phase anti-unitary, phase anti-unitary. When you pop that phase over the anti-unitary, it conjugates, and so then you get 1. So j squared is cannot be fiddled with by means of multiplying j by a phase in this case. So there's this extra invariant, so to speak, this phase of j that's equal to j squared. But then there's something else, which is that, see, we know that j is anti-unitary, so that we know when you pass this phase, which I'm calling c, through it, it gets conjugated. But we also know that this phase is j squared. And so j squared commutes with j. So this phase also commutes with j. So the phase both conjugate commutes, I don't know if there's a word for that, and commutes with j. So the phase has got to be real. So the phase has got to be plus or minus 1.
Okay.
So you have 2 options in that case. So there's some interesting structure here.
Well, okay, so it sounds like you said that this twofold classification gives you a threefold classification.
It's going to in a minute. Yes. Yeah, that's right.
I mean, I thought you already sort of said that.
Well,
okay, you go ahead and say it.
I mean, I've told you all sorts of things. I'm sure I've told you, but in the talk, I don't think I've said anything about yeah. So, okay, well.
I mean, you got me wondering whether it's a coincidence that you've got 3 of those classes and you've got 3 things to put in those classes, but go ahead.
Well, this is a threefold classification that's not the same as the threefold way, but it's it's 2/3 equal to the threefold way. So if you have a symmetry I'm just repeating myself. If you have a symmetry that squares to 1, either it's implemented by a unitary, which without loss of generality squares to 1, or it's implemented by a unitary, and then it's either squares to 1 or to -1. Okay, that is some threefold classification. Yes. but it's not the famous threefold way. Anyway, so if you have, so then you know all this stuff, but if you have an anti-unitary that squares to 1, then it acts a lot like complex conjugation. In particular, you can look at the vectors in your complex Hilbert space that are fixed by it.
Are you trying to hint that this is going to connect to Dyson's thing of that threefold classification?
Yeah, I'm
okay.
Yes, yeah.
Okay,
I'm explaining the threefold way here, but yeah.
Okay. No, this is good. This is good. Go ahead.
Yeah. So if an anti-unitary has j squared equals 1, then its fixed points form a real subspace, and it's a real Hilbert subspace of your complex Hilbert space. And your original complex Hilbert space is the complexification of that. So this is how the reals get into physics. Well, this is how real Hilbert spaces get into quantum physics, so you could say.
Yes.
Not that the reals weren't already in physics.
Right.
And then on the other hand, if we have this anti-unitary on our Hilbert space that squares to -1, then we get an action of the quaternions on our Hilbert space, where we use ordinary multiplication by I, and this J is our J, and we get a guy called K, which is I times J, and they will generate a copy of the quaternions. So then we can promote our complex Hilbert space to a quaternionic Hilbert space, which is a thing, which is a well-defined concept. And then our original Hilbert space is an underlying complex Hilbert space of that. And again, I just for fun decided to point out to people who may not know so much algebra that you can also think of this way that you get back your original Hilbert space as a product, as a kind of tensoring process, where we're like reducing the what do we call it? Reducing the algebra that acts instead of boosting it up.
So again, in some vague sense, it sounds like you're saying that, being a symmetry, which you start out thinking that that's like a commutativity condition, but then because of the phase ambiguity, it actually allows it to be some kind of anti-commutativity as another option or something like that. I mean, is that roughly on the right track? That's part of what's
well, it's certainly anti-commuting.
quaternionic. Yeah.
Yeah, it's certainly this quaternionic case, the symmetry anti-commuting with yeah, that's right. Yeah, there's more stuff to say that you just raised a point that
I raised it very uncertain, but yeah, go ahead.
Yeah, no. If we keep that in mind, we'll notice that I'm making some simplifying assumptions, and that should be good to not make. So okay, so we get R, C, and H all showing up, and here I remind people what I mean when I say division algebra, which I mean is a real associative division algebra.
Yes. And
then Frobenius classified them, I guess, around 1898. I just happen to know because I've been preparing for my talk. That's what Frobenius looks like. So then what I say is, okay, now let's keep that stuff in mind, and then let's think about irreducible unitary representations of groups on Hilbert spaces. So one thing that I would, sort of say when I have enough time, I've given this talk twice. If I have enough time, I point out that we shouldn't just think about unitary representations of groups now, because we've just learned that anti-unitaries are also perfectly valid symmetries. So, I mean, the natural concept of a group acting on a Hilbert space is actually a group acting as either unitaries or anti-unitaries. Well, I mean, the natural one from this physicsy point of view. And actually, Greg Moore, in his course notes on this stuff, he studies those type of representations extensively. And so everything gets a little more interesting, even more interesting when you start analyzing those. But I'm going to just not turn up all the knobs to full intensity and just ponder ordinary irreducible unitary group representations.
Okay.
And how they interact with the stuff that I just talked about.
Yes.
Okay, so on the one hand, we've got Schur's lemma. It says that when you have an irreducible group representation on a Hilbert space, or a complex vector space really, but on a Hilbert space, the only unitary operators that commute with all the rho G's are phases. Now, one thing that you just hinted at is that, again, saying commute here might be something you'd want to weaken. You might just be interested in ones that commute up to a phase. I mean, those would still be interesting. Also, and another thing I said is, I forgot to say back here, is we should have looked at projective representation. Sorry, and Greg Moore does that too. So we don't need this to hold on the nose. This could hold up to a phase as well. So if you're really trying to make, because physicists tend to make these simplifying assumptions, skip out on some possibilities, and then later on they learn, oh, nature actually exploits all the possibilities. So projective unitary representations are incredibly important, but also Greg Moore is arguing that you should think about projective unitary / anti-unitary representations. So anyway, there's lots that you could do here, but I'm just looking for unitary operators that commute, and I'm saying, well, that's not very exciting. You just get phases. But the excitement by contrast, happens when you look at anti-unitary operators that that commute with every operator rho of G, when rho is a sorry, I'm trying to mess around with my controls here. I did the wrong thing. Let me do what I actually wanted to do.
Okay.
So Dyson shows that if you have an irreducible unitary representation of a group on a Hilbert space, then there's a trichotomy that exactly one of these holds. So either there's an anti-unitary that squares to -1 that commutes with all the rho G, or there's an anti-unitary that squares to 1 commuting with all the rho G, or there's no anti-unitary commuting with all the rho G. So if I didn't demand that this was an exclusive or, that would just like instantly follow from the stuff I've said, because we already know. But so the only extra meat to this theorem, besides what I've already said, is that you can't have both an anti-unitary that squares to -1 and an anti-unitary that squares to 1 on an irreducible group representation. So I think if you assume that you've got both of those, you probably do something like you multiply them and you get a unitary, and then you proceed from there somehow. Get yourself into trouble, show that this representation couldn't have been irreducible.
Right.
So it's a trichotomy.
Okay.
And so in case -1, our representation was secretly a representation on a quaternionic Hilbert space. In case 1, it was secretly a representation on a real Hilbert space that we've complexified. And in case 0, neither of those are true. And so some people slightly confusingly call this representation complex, then, meaning that it's like really, really, really complex. So that's Dyson's classic threefold way. And so as an example of this that you may know already, it's good to look at like the irreducible representations of SU2. So they're classified by this spin. And it turns out that all of them have some anti-unitary that commutes with everything. So that is the complex case never shows up. They're all real or quaternionic. And they are real when J is an integer, and they're quaternionic when J is a half integer. I once wrote I have an article on my website called something like Symplectic Quaternionic Fermionic, where I was like trying to correlate those three concepts to this case, to the half integer case, to this case here, and then there's like the real orthogonal bosonic case. So for people who are less expert on group representation than you, I point out that like the spin 1 representation on C3 is really just coming from a real representation on R3. So it's really just the ordinary rotation group is acting on R3, and SU2 is double covering it. That used to like mystify me when I was learning physics, like, because on the one hand, they sort of say, oh, the spin 1 representation, that's just like normal. You're just like rotating stuff in 3 dimensions. But then for some reason, it's 3 dimensions in C3 instead of R3. So it's sort of like, yeah, I understand the vector in R3 is like a direction that an angular momentum could point. But now you're telling me a quantum state of a spin 1 particle is sort of like that, but it could be pointing in a complex direction. So even that like supposedly intuitive case is not so intuitive if you really think about it for a minute. But well, anyway, I feel a little happier about it now. There's like there is a real representation working around. I mean, I'm not completely happy. Why do we complexify it? But anyway, there's still mysteries to be found there. But so that's that case. But then in some ways, like the more thrilling case is the half integer case. So like if you take the spin 1/2 representation of SU2 on C2, then that's actually coming from a quaternionic representation of SU2 on the quaternion. So C2 turns out to be the underlying complex vector space of the quaternions. And I even got good mathematicians getting confused about that because what's going on here is that SU2 is the unit quaternions, and that's how it's acting on the quaternions. But to get things to work out, it has to be acting as multiplication on one side, and then the way that you make your quaternionic Hilbert space into a module of the quaternions have to act on the other side so that SU2 actually commutes with the quaternions. So luckily there are two sides on which it can multiply a quaternion, so it all works out.
Sorry, that's sounding, there's something there sounded like there was some SO4 thing going on there or something like that.
Yeah, it's true. There's SU2 times SU2 acting on the quaternions.
Again, I should know this, but I haven't thought about it in a while, so I'm just asking.
Yeah, this is the best way to prove that SU2 times SU2 covers SO4. So you can show that SU2 times SU2 acts on the quaternions, preserving the real inner product.
Yeah.
And then you can check that map. It's pretty easy to check that map is 1-to-1. Well, sorry, it's almost 1-to-1. It's
almost 1-to-1. Yeah,
2-to-1. It's locally 1-to-1. And then because SU2 times SU2 has dimension 6, and so does SO4, then you can. That makes it fairly easy. I'm not going to do any proofs for you. It's going to make it really easy to show that that's onto SO4.
Right.
And so then that's like a good way to see that SU2 times SU2 is a double cover of SO4. Yeah. So this is wonderful in lots of ways, but one of the cool things that I think physicists never talk about is that you could think of spin 1/2 particles as quaternions if you wanted to. From that one thing that's sort of weird from that point of view, if you think about it from that point of view, which they never want to think about, is that like you can think of them as quaternions, and then you get to pick what the complex structure is. That you get to pick which quaternion you're going to take to be your multiplication by I. So you have like this funny SU2 gauge freedom of deciding how you're going to.
So sorry, just very naively, part of what's going on is that the half integer irreps are even dimensional. That's part of what you're saying.
Yeah, that's right. Yep. Right. Yeah, they have to be for this stuff to be true. Yeah.
Okay.
Yeah. So right. So. Yeah. So the even ones are odd. Yes. Okay.
Right. Exactly.
Yeah. So okay. So that's an example that physicists are subconsciously familiar with. But it's a very general phenomenon, and so for example, suppose you got a unitary representation of any compact Lie group. The only thing I'm going to use the compact Lie groupness for is that that's a situation where we know that the unitary representation is completely reducible. You can break it down into a direct sum of irreducibles.
Yes.
Which I'm doing maybe for simplicity or something. Well, it's important, I guess. No, it actually is really important. So then what we could do in that situation is we could take our representation and write out the sum of all the irreducible parts of it that are quaternionic, and do it for all the irreducibles that are complex and all the ones that are real. And so it gives a canonical way to decompose our representation into a sum of three representations. So every unitary representation that's completely reducible gets to be canonically 3 graded. And the other type of thing that I'm not exposing my poor audience to in my talks is that we're not even using too much about group representation theory here. We're using the fact that like the category of these representations of these groups is some kind of semi-simple
Yes.
category. We've talked about that before.
Yes.
So,
Yes.
I mean,
Yes.
that's what I really
The endomorphism algebras of the irreducible objects have these.
have these 3 forms. Yes.
Yeah,
Never-
because right. There is something about, right? So have you already said this out loud, that the endomorphism algebra of an irreducible object is going to end up being a division algebra or something like that?
That's true. Yeah. The one reason why I'm not saying that as much as I could is that, I mean, that's the version of Schur's lemma that applies to any old field.
Yeah.
So if we took a completely real centered viewpoint, then, and we were like classifying, we were thinking about like irreducible representations of groups on real vector spaces, then you'd see these 3 division algebras popping up right away from Schur's lemma.
Yes.
So in some sense, I'm like tying one hand
Basically.
behind my back here by trying to explain it all, starting from the viewpoint of representations on complex vector spaces.
Well, I mean, that might also be a good viewpoint. I'm just less familiar with it, maybe.
Yeah, with physics, from
but-
physics, it's sort of the viewpoint that they want to take.
Yes. Yes.
In some sense, the fact that you're tying one hand behind your back that way makes it like, it's like Houdini. It like makes it all the more impressive that you get to the threefold way, that you get out you escape from the complex numbers and you get these 3 real division algebras showing up. I still don't understand it as well as I like, because you can see something funny is going on is that so like we started with these representations on complex vector spaces, and some of them are underlying representations of quaternionic representations, and others are the opposite of underlying representations of real representations.
Yes.
So you have to sort of get to the complex numbers either from a forgetful functor or from a free functor.
Right, right.
And so it's sort of, it gets more interesting when we get to the tenfold way, because the same stuff happens, but there's like more, there's more of it going on. So anyway, so yeah, it's interesting. And it would be nice to really straighten it out really well.
Yes.
So I make up this set that I call 3 in Roman numerals.
Yes.
Of the numbers -1, 0, and 1. And just for fun, somewhat for fun, I point out that that's a monoid under multiplication. And
yes.
So that these representations of compact Lie groups are 3 graded, and that 3 grading is getting along with the tensor product of patients in this following sense, that you would expect when you were talking about like tensor products of graded vector spaces, but this is a monoid, a graded vector space. Since my audience is less sophisticated in monoid graded representations than you are, I would like to point out that this is a spiffy way of saying that, like, if you tensor 2 quaternionic representations, you get a real one. If you tensor a real and a quaternionic one, you get a quaternionic one. If you tensor anything with a complex one, you get a complex one. So complex ones sort of eat the other ones.
Yes, I may have already asked this before, but I mean, at one point you drew this picture, like at the very beginning of today, you drew this picture of 8 things around the perimeter and 2 in the middle.
Right.
But here
Where-
there's a picture of like 2 around the perimeter and 1 in the middle or something like that.
Yeah.
Is that a parallel picture or something? I don't know.
Yeah, it's definitely present. So so the ones we're talking about now, the 3 of the threefold way, are
So the center absorbs things in this.
the center absorbs
these
things in the tenfold way, yeah, and the center, and then in the threefold way, the guys that show up are the super division algebras that are purely even, that have no odd part, and those are just R, this C here, and this H. And so this 3-element monoid is these 3, and that's a submonoid of this 10-element monoid that I'm going to talk about later. Yeah.
Okay.
So it's cool how it works like that. Right. Okay. So here we are.
Okay.
Okay. So now we're going to we're going to like copy these ideas and do the tenfold way. So first, for physicists, I want to give like a physicist absorbable description of the tenfold way. So the idea is that we could imagine that we're interested in charge conjugation and time reversal symmetry. And we could imagine that we want to assume that they are commuting anti-unitary operators.
Yeah.
And then, which was fit in their physical effect, they square to the identity. So as the anti-unitary operators, then they could square to 1 or -1. So you could have time reversal symmetry of either of those 2 kinds, or you might not have time reversal symmetry.
Yes.
Similar to charge conjugation symmetry. So that gives you 9 options. But then it turns out that there are physical systems which only have a combination of both charge conjugation and time reversal symmetry. That is, you have to switch particles and antiparticles and reverse the direction of time. And in the condensed matter physics, they call that S symmetry. And it turns out that you should think of it as unitary, which would make sense when it was actually equal to C composed with T. But here we're talking about the case when it's not, when it's just by itself. But for some reason, we'll still assume it's unitary. And then we assume, well, then we saw without loss of generality, we can assume that it squares to 1. So that's the 10th option. That's the weirdest option. So this looks like very much like not 10 is 9 plus 1 when you think about it this way, which Gregory Moore points out that like sometimes 10 looks like it's 8 plus 2, but sometimes it looks like other things. Sometimes we just saw a minute ago, sometimes it looks like 7 plus 3. We saw the 3 even division algebras. Yeah. But he mentions that, but I don't know if he mentioned this one. Sometimes it looks like it's 9 plus 1. So his argument is that these types of things make you realize that the 10 is a good idea. It's not just like 8 plus 2. It's there are various patterns at work.
So the S option is it really seems like an extra option off to the side. It's not like a peculiar duplicate of one of the other 9.
No, yeah, there's something that has no C nor T symmetry nor the combination of both. That's what I maybe should have said. So that's one of the 9. Like system with none of this kind of symmetry. But then there's this 10th one has like, morally speaking, CT combined symmetry, but not separately C or T symmetry.
But it almost does seem like the one that S has the most affinity to is that one that you mentioned, the one with neither T nor C.
Yeah, so.
I'm not sure.
Yeah, no, you're right, actually. I mean, I'll just show you. So the one with none at all is the one corresponding to the Clifford algebra that's just the complex, the even super division algebra, the complex numbers.
Uh-huh.
And the one with this S symmetry is this other complex Clifford algebra. So they are relatives of each other. They're those two. I mean, I don't know if that proves anything, but that it shows that you're right that those two options are more like each other than the others.
Okay, so you said that the three and the fourth one are right down the middle. That means is there three on the left and three on the right, or is it mixed up? Or
People.
Sorry, are you talking the
People
audio?
draw this chart in another nice way. If
I
you
think
look
the
at
audio
this,
just glitched.
you hear me now?
Yeah, I think so.
Okay. Yeah, it didn't freeze up here, which is why I.
Right, but I don't think I could hear some. I think I missed something you said.
Oh, I was just going to say that there are some other. You were asking like, oh, is there something like the left side and the right side? And yeah, stuff like that. So if you notice that on the if you look on these left three, you've got C symmetry.
Yeah.
But possibly not T symmetry. And also on the right side, you've got C symmetry, but possibly not T symmetry. But on the left side, C squared is equal to 1. And on the right
side, so the columns looks like the threefold classification for C.
Yeah. And then another cool part, though, is that if you can think of rows. So that was like a slightly bent column. Here's a slightly bent row. I mean, it's just as much of a row as that other thing was a column. This is the ones that have T squared equals 1.
Yes.
These are the ones where T squared equals -1. And these are the ones that don't have any T.
Yes.
So there's some people who draw this chart as more of a square.
Right.
You make this column, make these columns and these rows just line up nice and square, and you get a square with 8 entries and like a hollow middle.
Right. So like, I mean, you were mentioning 7 + 3 versus 8 + 2 and all that, but I was sort of asking about 9 injecting into 10 versus 10 surjecting down to 9. So, 10 surjecting down to 9, that's sort of like the 3x3 tic-tac-toe board, but with 2 in the center instead of just 1 in the center or something like that.
Yeah, there are people who draw things sort of like that. Yeah, but yeah, you're right. This is really fun to think about. All these.
Okay.
Placing the pie, quite literally.
Okay.
The pie chart. So, okay.
But meanwhile, there is that other very circular interpretation of the perimeter, and that really has to do with the Clifford clock.
Yeah, I'm getting there.
Okay, but it's just interesting that right. That's weird that you can have the circular clock interpretation overlaid over the rows versus columns square interpretation. That's weird that they coexist like that. But okay, go ahead.
Yeah, I mean, there's a way to think about that Clifford algebraically as like stuff that happens when you keep on throwing in these square roots of -1.
I guess one thing that I sort of didn't say out loud, but I almost said it, was that 9 is a retract of 10.
You did say it, but let me think about what the hell you meant by that.
No, I didn't say 9. I didn't use the word retract, I don't think, but now I'm using it. 9 is a retract, 9. Am I saying that's right? Yeah. 9 is a subset of 10, but the 10 retracts onto the 9.
Oh, okay. Yeah, you said surject and include.
Yes, surject, but yes,
almost
retract.
Yeah. Oh, but they fit together well as a retract.
I don't know what that means, but I just wanted to mention it. Go ahead.
Yeah, it'll be fun to think about all these things more. I'm going to think about all this stuff more category theoretically at some point, and there'll be like two categories of categories of representations, and yeah, all these maps between. Yep. Okay, so I have had trouble finding like a nice chart listing materials of all the different 10 kinds.
Yeah, I was really going to ask you about this. How literally should I be taking this idea of condensed matter? You know, is there really, can I hold these in my hand? Would I want to?
Some of them you'd have to have like gloves on.
Right.
A lot of them are at very low temperatures, but a bunch of them have been made. A bunch of them only work easily in other dimensions. So people do a lot of thin films or one-dimensional systems.
Yes.
To make these things.
Yes.
But some
Sorry,
of
is there a name for that? Oh, filaments? What's the name for, you know, film? You call them filaments if it's one dimension?
Wires.
Wires.
Yeah.
Okay.
Sometimes wires.
Wires. Yeah, okay, wires. It's good.
This thing isn't really like, this is a very small wire. So there's this molecule called polyacetylene. This is one of the two forms of polyacetylene. It's a carbons and hydrogens, and people noticed that this molecule can be a superconductor at low temperatures, and they got so the electrons.
When did they notice that? Maybe it's very, very low temperatures. Is that what it is?
It's pretty low temperatures. Yeah, I forget how low actually.
Okay.
But it's not very high temperature. It's not what you call high temperature superconductivity.
Sure.
And they got very puzzled about how it works, and I wish I understood it better, and I don't, but there's a model of it, which is like a simplified model where you just like assume that an electron can be sitting at any one of these carbons, and it can have spin up or spin down, something as simple as that, I think, and then it can hop to nearby carbons and in a quantum-y way. And so in the simplified model, I wish I understood this. I don't, and I should. So
I mean, when you talk about, right, I mean, it seems like, you know, for these ones that I want to actually hold in my hand, perhaps gloved hand, those might not be fundamental examples.
well,
because, you know, things you hold in your hand, those tend to be complicated things with, like, you know, many kinds of particles blended together or something. So they're not really fundamental.
Well, condensed matter physics is never
fundamental.
Never really fundamental. So what you do is you try to build a very clean chunk of matter where most of what's going on is described by some pretty simple theory, simplified.
Okay. So that's part of what condensed means, I guess.
Like abridged.
Yeah, maybe. Okay.
Reader's Digest condensed. Yeah. So I never thought about it that way, but that's what they think it means. But I guess already the process of freezing is already beginning.
I mean, you're really making it sound like there really is this extreme opposite cultures of condensed matter theorists versus you know, what's that other particle physicists? Like those are like really fundamental.
Yes. So the famous condensed matter physicist Anderson launched many salvos against the particle physicists.
That sounds fun. Yeah,
he was fun. When I was young, I didn't like it because I was a particle physicist. And now I like it. He was like arguing that like all physics is like condensed matter physics. And
well, yeah, I mean, you can say
fundamental physics, you're just like fooling yourself.
Yeah, I mean, I think you can sort of find currents like that in particle physics of, you know, particle physics. He says that, you know, that it isn't really particle physics, that it's, you know, that there's nothing fundamental. It's all turtles all the way down or something like that.
Yeah, exactly. Yeah. Yeah, not many.
bootstrap or something like that, but yeah.
Oh, yeah, that's a good point. Yeah, that would be an example. Yeah, I was going to say there are not too many theories where people try to like make good on that. Turtles all the way down.
Well, renormalization and bootstrapping and all that, it's a theme that shows up.
Yeah, yep. So anyway, so this is supposed to be a physical system that has only this combined symmetry called S with S squared equals 1. This is
So is renormalization, is that a more fundamental thing in condensed matter physics than it is in particle physics or something like that?
I can't answer that, but it's very fun. It's very fundamental. I'd say it's very fundamental in both, actually. But maybe arguably in condensed matter physics, maybe it's more fundamental because in condensed matter physics, you very often have a system that you know is too complicated to fully describe. You admit it flat out, and then you use the renormalization group method to show that when you view it a larger length scale, it can be described by a simple theory. Well, you show it or / hope it, and you study how like various kinds of things that you might not know about get washed out at larger.
Yeah.
So in some sense, it's more fundamental. So as in particle physics, you know that the renormalization is important, but you might still cling to the hope that like you know what's happening at the shortest length scales.
Yeah.
Yeah, I think that's right. Yeah, so this attitude towards renormalization sort of spread from this attitude that we're dealing with so-called effective theories, not the true theory, but some limit of the theory. That sort of spread from condensed matter physics. Kadanoff's work on the renormalization group to particle physics. So nowadays, like if you say to particle physics, like you can't prove yet that quantum field theory is consistent. You don't even know that the standard model is a mathematically consistent theory. They have this annoying way of getting out of it where they say like, we don't care. It's just an effective theory anyway.
Yes.
Which is annoying because it means that like they could say that forever, right? They never need to prove their theory is consistent because it's always just a. Right. Whereas for mathematicians, we don't really care if it's true or not. We don't want to study it and see if it's consistent or.
Right.
Just like saying, I don't care. It's sort of irritating. Okay, so here's the more mathematical outlook on the tenfold way. So we're going to work with super Hilbert spaces now, which are just Hilbert spaces that are Z2 graded. And study the stuff that I did for the threefold way, stuff I talked about. Now do it in the super Hilbert space context. Now for the physicists, I have to either reassure or warn them that there are different physical ways to make use of super Hilbert spaces. And if you're a physicist, you might instantly think that the even part means states of bosons and the odd part means states of Fermi. And that's certainly an allowable way to use super Hilbert spaces. But a very interesting thing is that condensed matter physics doesn't mainly use super Hilbert spaces that way. In fact, I think they almost never use super Hilbert spaces that way. They probably may not call them super Hilbert spaces, but what they would often do is they would let one of these summands be a Hilbert space for particles and the other one be a Hilbert space for antiparticles, or in condensed matter physics, where your particles often are just quasi-particles to begin with. The antiparticles may just be holes. That is, they may not be fundamental antiparticles, but they're just absent particles. And I'm mentioning with this picture here that that's a pretty natural thing to do, even whenever you're dealing with like a quantum field theory, or like, sorry, let me not talk about quantum field theory. When you're talking about like a a single particle in special relativity, its momentum is constrained to lie on this mass hyperboloid, but that has
Yes.
two components. And
Yes.
so if wave functions are L2 functions on the mass hyperboloid, it's very natural to think of that Hilbert spaces as Z2 graded, as having these two parts. And people do that. Think of
Okay.
one particles and the other is anti-particles sometimes. Okay, so then in this situation, so I'm not going to stick to the physics interpretation of it. I'm just going to go do the math now. In this situation, when you have super Hilbert spaces, it's very nice to focus attention on even and odd operators. And you can have even anti-unitary operators and odd anti-unitary operators. And I'm going to call the even ones T, because that is often how because in physics applications, that's how they are, what they often could be in condensed matter physics. And the odd anti-unitaries, I'll call them C. But I'm doing math now, so that is, I'm not promising anything about what the application of the math is, because there's some subtleties and flexibilities about how you would apply it. Okay, so then you can, since we're going into this Z2 graded world, we should look at Z2 graded groups as well. And then you can have Z2 graded groups acting.
I mean, could I just, by a Z2 graded group, you really just mean that there's a homomorphism to Z mod 2.
Yep.
Okay.
Yeah, so these are, I'm not calling them super groups because in
Actually, wait a minute. So, but that makes it sound like I'm claiming that G0 and G1 are the same size. Is that right?
if there's anything at all in G1, then they have to be the same size. Yeah, you could have one where G1 was empty.
Sure.
Yeah, but apart from that, then G1 is like a Torsor for G0, I guess is what it's got to be.
That sounds right, I think. Yeah.
Yeah, that'll be true. Yeah.
Okay.
Yeah, super Hilbert spaces don't need to be the same size, and
Sure.
the super groups or Z2 graded groups do.
Okay.
I was just saying, I'm not going to call them super groups because a Lie supergroup is some kind of super manifold that has a group structure. So that's something else.
Yeah.
Okay, so a unitary representation of a Z2 graded group on a super Hilbert space is just an ordinary unitary representation on the underlying Hilbert space that gets along with this grading in the way I'm indicating here. So odd group elements interchange the even and the odd vector, map even vectors in your Hilbert space to odd ones and vice versa, etc.
Yes.
Okay. And then we say that such a thing, using more category theory, we could say all this much faster. Okay, but I'm not doing it.
Sure.
So similarly, we can say such a representation is irreducible if the only closed subspaces that are graded subspaces, that is some ends of an even and an odd part, that are invariant under the group operation are the zero and the whole thing. So it doesn't need to be irreducible, as the underlying group representation might not be irreducible, because you could have other subspaces that don't sit smack in V0 or that don't break up as a sum of an even and an odd part. They could sit sort of diagonally in there.
I mean, you've probably mentioned this vague idea before, but I'm not sure I've really thought about this. But okay, go ahead.
Yeah, so we're just sort of systematically waving the wand of Z mod 2 grading on every concept here.
Okay.
Including subspace. So, okay, so then we copy Dyson's threefold way in this Z2 graded context and try to see what happens. So we look at irreducible unitary representations of a Z mod 2 graded group on a super Hilbert space. And what we do is we look at we take such a thing and we look at its commutant, by which I mean the set of real linear operators that commute with all the unitary transformations in our group action. And so we see that like different types of things are possible. So you could have an even anti-unitary that in the commutant. You could have an odd anti-unitary in the commutant, or not. And so those anti-unitaries we've seen already. Well, I guess you have to enhance the argument a little bit, but it's the same type of argument. They have to either square to 1 or -1. So you get a 9-fold classification of what kind of anti-unitaries can commute with all your group transformations. And then there's this 10th kind that we've seen before, where you don't have either of those anti-unitaries in the commutant, but there's an odd unitary that in the commutant.
Can I ask a stupid question here?
Yep.
Is this secretly just the super version of that discussion that we had about, you know, endomorphism division algebras? As soon as you start talking about commutants, that makes me think you're talking about endomorphism algebras, but maybe endomorphism super algebras or super endomorphism algebras or something like that. And maybe
So again,
I didn't think this through, but is that secretly what's going on?
I think so. Yeah. So again, discussion would be much clearer in my mind and much easier to explain really, really clearly if we'd been working with real representations on real
Right.
spaces.
Right.
Then what you say would be exactly right. We would just look at the commutant of an irreducible representation, and we could show that had to be a real super division algebra.
Yes.
Just copying the proof of Schur's lemma.
But then, you know, taking the complex viewpoint as more basic, just maybe throws an extra wrench into the question.
Right. Yeah, that's right. So like, yeah, so there's a part of me that wishes that like I wasn't talking to any physicists and I could just like give this as a pure math talk and then it would like hang together better. Because we wouldn't be dealing with this business of like seeing the ghosts of the real superdivision algebra lurking in this context that where we're acting like we're talking about complex representation theory, which makes it more complicated. I already sort of said how it makes it more complicated in the threefold way. Like sometimes a complex Hilbert space will be the underlying one of a quaternionic Hilbert space. And sometimes it'll be the overlying Hilbert space of a real.
Sure, but I mean, that's very fun too, but.
Yeah, it's fun, right? But it's like, yeah.
I mean, there may be something very important about thinking of it that way. I'm not sure yet, but we'll have to think about it.
Yeah. I think it is important. It is important. Yeah, but yeah, I mean, if I were allowed to give like a longer talk, I would like first do all the real case and then I would do all the complex things on top of it. And that would be like the clear way to think about it. Yeah. But I haven't even that would require that I understand it a little more clearly than I do.
I'm just having trouble getting it to make sense that like left adjoints are positive and right adjoints are negative. That's not, I don't know what's going on.
Okay. Yeah, that's weird. So there are 10 kinds, which I've listed. And so let's call the set of them 10 or X or whatever.
Okay.
And so just like we did before, if you have a unitary representation of a Z-mod 2 graded group on a super Hilbert space, if it's completely decomposable into irreducibles, then you can put this 10 grading on it.
Yes.
Where you chop it up into the 10 different kinds of irreducibles. And then what I'm claiming here, which you already have seen me claim before, I guess, or something. I don't know. Somehow you took it for granted. Yeah, I've talked about this stuff before with you, I guess, is that there's a way to put a monoid structure on the set 10 that makes tensor products of representations. Tensor producting representations is compatible with the 10 grading that they naturally get.
Yes.
And so then for people who are suffering through this talk, I say, okay, well, how do you do that? Well, it turns out that this guy 10 is the disjoint union of Z mod 8 and Z mod 2 with this funny addition that, like, you add the normal way in either of those two groups, except when you're trying to add something in Z mod 8 and something in Z mod 2, and then you add them willing, and then you mod out by 2, which makes sense because 8 is divisible by 2.
Yes.
And so I call these 10 elements 0 through 7, and then like boldface 0 and boldface 1.
Yes, that's good.
Some examples, and like the boldface guys dominate the non-boldface ones.
Yes, yes.
Of each kind. Yeah, you're familiar with this for some reason. I don't know why, because I've been talking to you. So here that thing is.
Yes.
And here it is in conjunction with this classification of the possibilities for T and C. And it's not, it takes, right now, it takes me work. It'd take me real work. It would take me real work to show that these correlate with each other in this particular way.
Mm-hmm.
So ideally, it would all get smoother and smoother. So then I admit that this 10 element set is also the set of super division algebras. So those are super algebras that have this property that any non-zero element that is homogeneous has a multiplicative inverse. So you tweak the concept of divisionness. And so here's an example that you're familiar with. I'm sure we've talked about it. You can make the complex number into a superdivision algebra in 2 different ways. One where it's all even, and one where the reals are even and the imaginaries are odd.
Yes.
And so Wall almost did it, but I don't think he did it. And Dolan, I know, did it, which is to actually classify the superdivision algebras. And so you get them by taking these. You get 3 of them by taking Clifford algebras and throwing in more. Just throw in more and more. Oh, sorry, you get 4 of them. You can throw in more and more square roots of -1.
Yes.
That are odd. And you can throw in at most 3 and still get a super division algebra. You should be imagining that chart. I guess here we're going down going around the outer rim of that circle.
Yes.
But when you hit cliff 4, that's not a super division algebra itself. And so you could say okay, I'm going to go the other way. I'm going to throw +1. You can do that.
Again, I'm not sure if I missed,
cliff
my
-1.
audio glitched. I'm not sure if I missed half a sentence there.
Oh, I'm saying that we could get more superdivision algebras by looking at these other kind of Clifford algebras where you can throw in square roots of 1 instead of 1. And I call these Cliff with a negative index because things work eightfold.
We must have talked about that. So you're making it sound like, clockwise is adding square roots of -1 and counterclockwise is square roots of +1 or vice versa or something like that.
That's right.
And they just sort of cancel out by Morita equivalence or something like that.
Yeah, we didn't quite come out and say it that way, but we did. I think we, yeah. So I think we said like that. Yeah, people certainly know that like there's this Clifford algebra with a square root of 1 and a square root of -1 thrown in, and that's a
It's
2
like
by
split, called the split thing or something like that.
I don't know. I would call this the split one. But if you throw a square root of 1 and a square root of -1 in your, then you get the 2 by 2 matrix algebra.
Yeah,
And
that's split in some different sense, but go ahead, yeah.
Okay. So that's Morita equivalent to the real numbers. So that what you're saying is that if you throw in a square root of 1 and then throw in a square root of -1, you get your Clifford algebra has gotten fatter, but it's still Morita equivalent to the
Yeah.
So we can throw in one of them or two of them or three of them. And we get these algebras, R plus R, M2R, and M2C, made into super algebras in certain specific ways. And then when you get to Cliff -4, you run out of steam in a certain sense. So
Yes.
Cliff 4 and Cliff 4, they're not super division algebras,
Yes.
but they're both the purely even quaternions tensored some matrix super algebra. So then we've gotten all these guys. Yeah, so these guys, we got the square roots of -1 thrown in here, these ones, the square roots of +1. This has something or other to do with this stuff when we were talking about that square.
Yes.
Columns. There's something going on there.
Something. Yes.
Don't fully understand, but I'm sure it's not a coincidence that this is all too nice to have any coincidences.
Yes.
So then the other two guys, the complex Clifford algebras, make up the other two superdivision algebras. So we get the one with a single. We get the complex numbers as a purely even. And then we could throw in a square root of -1. Or we could, I hope I said it. I didn't say it. No. Or we could throw in a square root of +1. It doesn't matter because you're over the complexes. And so then you get like the split complex numbers or whatever. No, I don't know what that's called. Anyway, C plus C. So yeah, so now we've got them all. And so it's not obvious how this Clifford algebra, how this classification of superdivision algebras maps onto this classification of possibilities for T and C anti-unitaries and
Yes.
So that is just a big calculation as far as anyone that I know knows. So that's it. And so I just will wind up by pointing out there like various things that I think somebody should understand better someday. So one of them is like why. Well, let's see. So there are very general reasons why when you start thinking about Morita equivalence classes of central division algebras or central superdivision algebras, I believe that there are general reasons why the division algebras show up. So I mean, there's this, in each case, there's like a theorem that every central simple algebra is Morita equivalent to a central simple division algebra. But
sounds very plausible. Yeah.
So that part I think of as, I mean, I think someone out there conceptually understands that. But why should you be getting, in this super case, why should you be getting Clifford algebras? I think maybe people sort of understand it, but that seems like a little more of a miracle to me. So like, why does the eightfold bot periodicity of Clifford algebras just happen to like beautifully match up with the periodicity in this Brouwer-Wall group, that the group of Morita equivalence classes of central, simple, real superalgebras. It seems like,
How did you describe the first one involving the Clifford algebra? What did you say that was?
I sort of said bot periodicity. So I'm using, I may be like using
Periodicity.
Morita equivalence in the concept to get them to say that the Clifford algebras are period 8. So in both concepts, I'm using Morita equivalence as my equivalence relation. So there is something in common there. But from one point of view, I'm saying like, all I care about is Clifford algebras up to Morita equivalence. And then I see Z mod 8 show up. And then in the other outlook, I say, all I care about is central, simple, real superalgebras. I know that's a bunch of adjectives. And I see Z mod 8 showing up when I look at those classified by Morita equivalence. So it's not a complete miracle, because as soon as you get into the super business, you get interested in stuff that squares to the identity. I should say that like some people have classified Z mod 3 graded so central simple Z mod 3 graded algebras. And then you see you don't get Clifford algebras. You get some weird kind of thing that has like cube roots of 1 showing up. So that sort of shows you something about why Clifford algebras are showing up in what we're doing here. Is that we have Z mod 2 is getting us very interested in operators that square to 1 or minus 1. But there's still mysterious stuff about it. I think it's especially mysterious when you think about Clifford algebras as being like related to rotation groups or spin groups in physics. Like, why are we getting this thing where like we started out studying super division algebras and then like bingo, we get the math that we need to study spinners. That's okay. So that's like one thing that maybe there could be like more clarification. Then I guess something like much more of a murky business is like, how are those two eightfold periodicities connected to these possibilities for anti-unitary operators that could act on an irreducible super representation? So for that, I just have to like calculate a way. So yeah, I guess those are some of the I think there's like philosophers have some concept they call like an explanatory debt, a debt.
Yeah.
So there's some kind of debts here.
Yeah.
Which is where, of course, I hope that mathematicians will come in and try to make it nicer. There's tons more stuff, but that's what's here again. So I seem to have eaten up almost 2 hours.
Well, that's fine. I'm very tired today by being my sleep schedule is out of kilter. So is there anything we should do before we quit?
Nope, nothing else. Nothing else. So someday I would like you to tell me some amazing thing. You about this. You already sort of did. You got me to think more about the patterns in this
Yeah.
picture. So that's already actually pretty good.
Let me
But
say
you-
one really stupid. Let me say one really
Mhm,
stupid
yeah.
thing. Just, this 3x3 square versus some period 8 circle or something like that. It just vaguely reminds me of stuff that I've been looking at recently when I look at my Gaussian designs.
Uh-huh.
I'm working over the Gaussian integers mod 3, like a 9-element square,
Uh-huh.
but it also acts like an 8 period 8 circle in some ways. Is it really period 8, or is it just 2 period 4s? I'll have to think about it.
Oh, you mean like the 4 edges of the square and the 4 corners of the square?
Yes, because I mean, in the algebra of the Gaussian integers, at least in some aspects of it, it's very hard to tell the difference between the diagonals versus the horizontals and verticals. They're actually on the same footing in a way. So there's like 8.
Huh. Huh. Up to isogeny or something like that. I don't know.
I'll have to think about it. I'll have to think. Just just going by very vague numerology and how this
Yeah.
pictures that you were drawing are reminding me of silly pictures I've been drawing.
Yep.
All right. Anything else?
Nope.
Okay. Thanks a lot.
Okay. So,
Okay.
yep.